The Allison engine's AE3007A series engine is classified as a dual-spool, high bypass ratio turbofan engine. A turbofan is a jet engine that uses some of its exhaust energy to drive a fan. This way it enjoys the advantages of a jet, which is higher altitudes and higher speeds, as well as the advantages of a propeller, which is better aerodynamic efficiency at low altitudes. In the engine core, air is sucked into the compressor through the intake. The compressor has two jobs. One is to ensure there is enough air for combustion even at high altitude. The other is to allow as much air as possible into the combustion chamber, allowing more fuel to be used, which produces more thrust. There are 14 stages in the compressor. Each stage consists of a stator blade followed by a rotor blade. The stators are shown here in blue. They are stationary and connected to the compressor case, also shown in blue. The rotor blades, shown in green, are connected to the compressor core, which is spinning. The purpose of the stators is to deflect airflow so that it hits the rotors at the correct angle. The rotor blades act as propellers, spinning at high RPM to push the air backwards through the compressor. Because of the shape of the compressor core, narrow at the front and wide at the end, the air has less and less room to fit through as it's being pushed backwards by the rotors. As a result, the air gets compressed as it goes from the first stage to the second, third, all the way to the 14th stage. With each stage, the air pressure and temperature increase. On their way out of the combustion chamber, the exhaust gases cause the turbine wheels to spin. There are two separate turbine wheels: the two-stage high-pressure turbine, connected by a shaft to the compressor, and the three-stage low-pressure turbine connected by a separate shaft to the fan. Each spool can rotate at a different RPM. This is known as dual spool. The fan has a much greater diameter than the compressor, therefore it spins at a much lower RPM. 100% fan speed is close to 8,000 RPM, while 100% compressor speed is close to 16,000 RPM. We use the N1 or fan RPM as a primary setting for thrust because it changes more between idle and full thrust, while the compressor speed between idle and full thrust does not change as much. At the front of the compressor, a tower shaft is geared to the compressor wheel so that when the compressor is spinning, the tower shaft is spinning, driving the accessories located underneath the engine. During start, the air-driven starter located in the accessory gearbox drives the accessory gearbox, which is connected to the tower shaft, which starts turning the compressor, drawing air into the combustion chamber. When enough air is drawn in, ignition and fuel are introduced, starting a controlled explosion in the combustion chamber. The exhaust gases drive the turbine wheels, and the engine starts to accelerate on its own power, accelerating the compressor, or N2, and eventually the fan, the N1. The exhaust gases exit the engine at a very high speed, creating a low pressure area around them. This pulls surrounding air into the flow, effectively taking an additional mass of air and accelerating it backwards, producing additional thrust without using additional fuel. This would be true even without a fan. This area where the air is accelerated around the engine is known as a bypass. A 5-to-1 bypass ratio means that 5 times as much air bypasses the engine as enters the engine core. This is considered a high bypass ratio. At lower altitudes, up to 80% of the thrust produced by the engine is produced by the combination of the bypass and the fan. At higher altitudes, as there is less and less air pressure, this becomes less effective, and only 50% of the thrust is produced by the bypass and fan. This means that 50 to 80% of the thrust is produced without using additional fuel. Let's take another look at the engine components. The shape of the intake is an expansion area, meaning that as the air enters the intake, the area available for it increases before reaching the fan, and so the air expands. Due to the expansion, the temperature through the intake drops by up to 10 degrees. This means that icing can occur if moisture is present, even though the ambient temperature is above freezing, up to about 10 degrees Celsius. The fan is nothing more than a shrouded propeller. It has 24 constant pitch blades rotating at up to 8,000 RPM. In the compressor, 14 stages of stators followed by rotors force the air backwards while the area available decreases, forcing the air to compress. If the airflow is disturbed, the air will tend to go from high pressure to low pressure, meaning from the rear of the compressor forward and out the front, causing the combustion chamber to flame out. This is called a compressor stall. To prevent compressor stall, the inlet guide vanes in the following 5 stages of stators can rotate, changing the blade angle, reducing the angle of attack, and therefore preventing the airflow from stalling. A momentary flameout can be relighted if the igniters are turned on. This is called auto relight. In the combustion chamber, high pressure air is mixed with a high pressure spray of fuel to sustain a continuous flame. During start, igniters are used to start the flame. Once the start cycle is complete, no ignition is used. The exhaust gases from the combustion chamber drive 2 separate turbine wheels. Finally, the exhaust gases exit the engine core through the forced mixer, which swirls the air and forces the hot exhaust to mix with the cold bypass air. This reduces the overall temperature of the exhaust prior to exiting the nacelle, reducing engine noise.